So, continuing the discussion on the classification of composite material. So, here we go with the second classification, that is based on reinforcement materials. So, as already we have discussed in the previous section, the classification of composite material based on a matrix like a matrix, ceramic or a polymer matrix composites. And in the polymer matrix composite, we can see thermoplastics as well as the thermosets, which can be used as a matrix material. So, depending on the properties required for a particular application. So, moving on to the second classification, so where the composite material are classified on the basis of reinforcement. Okay. So, reinforcement is the one which is going to decide the strength of the composite material as well as the interface. So, if you see here, the composite material are classified on the basis of reinforcement as particle reinforcement, fiber reinforcement and structural composites. So, when we say particle reinforced, or we, in other words, we call it as a particulate composites also. So, in that one we can say large particles and dispersion strengthening, or you can say small particles also. So, again depending upon the size of the particle, so particle composites, reinforced composites are classified into large and dispersion. So, you can say here, so particle reinforced composites. So, if it is a larger one, so then it is a randomly distributed. Even when it is a dispersion strengthening, the size of the particles are small and they are randomly distributed to act as a hurdle for deformation, thereby increasing the strength. So, next category we have fiber reinforced. In the fiber reinforced, we are going to have a continuous or a discontinuous. So, when we say a discontinuous, when we say a continuous composite material, so you can say here, so either the continuous fibers may be unidirectional or may be bidirectional as a mat. Okay, so we can clearly observe those things in the picture. Okay, so continuous, either it may be a unidirectional one, or continuous, it may be a bidirectional one as a mat material. Okay. So, in the second category we have a discontinuous or a short fiber, where in that one again those things are classified into aligned and randomly oriented. So, aligned means they are tailored for a directional property, and random means the properties will be randomly distributed throughout the directions. Okay. So, when it comes to the structural, so we are going to have a laminates and a sandwich. So, this is to ensure that the strength of the composite remains same in all the direction. Okay, plies of a unidirectional fibers are prepared and they are led in a opposite direction. Okay, so with the help of a glue, okay, again they are compressed to form a composite material which is having a strength in equal in all the directions. Okay, so like that, so we can classify these fibers in various categories. Okay, so reinforced composites into various category as follows. Okay, so moving on with the things. So what are the key features? Okay, so which are there in these categories? We'll see one by one. So we'll take the first and a bit famous one in this classification as FRCs, or you can say fiber reinforced composite materials. Okay, so these fiber material for this fiber reinforced composite material, so wood is the best example. So where, so these cellulose is going to act as a fiber, that is a reinforcement, and the lignin is going to act as a matrix material. Okay, so as already we know the roles of a matrix and the reinforcement, this lignin is going to bind these cellulose intact. Okay, so intact, giving a proper shape to the wood or maybe the plant. Okay, so these fibers like that is a cellulose is going to give a strength to the plant or maybe the wood. Okay, and whenever we talk about these fiber reinforced composites, so these are very famous in the specific strength and the specific modulus parameters. Okay, so what is the specific strength? So specific strength is nothing but a ratio of a tensile strength to the specific gravity, and the specific modulus is a ratio of Young's modulus to the specific gravity. Okay, so fiber reinforced composites are exceptional in these specific strength and specific modulus in the parameters. Okay, so we can see here again, so fibers are important class of reinforcement. They satisfy the desired condition, transfer strength to the matrix material. So performance of a fiber composite is judged by its length, as I said, L by D ratio, shape, orientation, composition of the fiber, and the mechanical properties of the matrix. The orientation of a fiber in a matrix is indication of a strength of a composite, that is a directional tailoring. Okay, so monolayer tapes consisting of a continuous or a discontinuous fiber can be oriented unidirectional, stacked into plies containing layers of filaments, also oriented in the same direction. So if you want the strength of a composite material to be in a one direction, so we can have fibers aligned in a one direction, or if you want to have a strength in all the directions, so then we can have a plies of a fibers which are oriented in a different direction, and then they can be formed. Okay, so in a bidirectional to give a strength in all the direction materials. So orientation of a short fibers by different methods is also possible, like a random orientation by sprinkling on to a given plane, or a addition of matrix in a liquid or a solid state before or after the fiber deposition. Okay, so even so we can have a discontinuous fiber also, which are chopped into a predefined length. Okay, so which are spread on the a layer of a resin. Okay, so again one more layer of a resin is provided, and it is compressed to give a particular shape and a strength to the composite material. Okay, so even whenever we talk about a fiber reinforced composite material, okay, so if there is a proper bonding, okay, so proper a strong interface between a matrix and a fiber. Okay, so the condition is the matrix should be of a quality to wet the surface of the reinforcement, then the interface will be stronger, then the strength of the composite material will be bit stronger. Okay, so as already we know, in this again fiber we can have a continuous, we can have a discontinuous. Again in the discontinuous we can have a uniformly aligned and a randomly distributed composite materials. Okay, so even we can have any type, like a biodegradable one, or a natural fibers, or maybe synthetic fibers also. So in order to have a fiber reinforced composite materials. And the second category is the laminated composites. Okay, so where laminated composites, if the in the fiber, okay, if the fibers are aligned in only one direction, okay, if there is a uniform alignment in one direction, then we are going to get a anisotropic property. Okay, so means so different property along different directions. Okay, so if the layers of the composites are stacked and bonded together in such a way that successive layers are there, fibers aligned in a different direction, okay, then the composite will be having a uniform strength and properties in all the direction. Okay, so means so wherever the application needs, okay, to have a strength in all the direction, okay, so there we can go for these type of composites. Okay, so where we have seen the sketches where the fibers are aligned in all the direction, so which is going to give us strength in all the direction. So we can say like laminar composites are found in many combinations, such as number of materials. Okay, they can be described as material comprising of layers of material bonded together. The structural application of composites are mostly in the form of laminates. Okay, so many a times the doors, okay, or the panels, okay, of these wardrobes and all are made up of these laminates. So laminates provide inherent flexibility that a designer exploits to choose the right combination of materials. Okay, so a lamina is a basic building block of a laminate. A lamina may be made up of a single material, okay, metal, polymer or ceramic, or from a composite material. So a composite lamina in which all laminates are aligned in one direction or parallel to each other is called as a unidirectional lamina. So where the strength is distributed in only one. Okay, so we can see the laminates like this. So the fibers are aligned in a different direction to give a strength in all the directions. So various such a hybrid laminates can be prepared for a practical application like a functional grade materials. Okay, so we say like a FGV. Okay, so functionally FGMs, functionally graded materials. So where it is useful in thermal applications and all. Okay, so aramid epoxy composites are commonly combined with the carbon epoxy composite to make a carbon Kevlar hybrid composites to obtain a cost effective composite with a superior compressive and impact resistance property. So here the aramid fiber is having its own property like a impact resistance. Okay, so epoxy are good in a compression, so combining those two we can get a superior quality in a compression as well as the impact resistance properties. Okay, so Kevlar fibers are inexpensive compared to carbon fibers and are effective in resisting the impact forces like a bulletproof glasses. Okay, so there we can go for a hybridization of these composites to have a different properties. So next one will be particulate reinforced composites, where we said it's a large particle or maybe dispersion strengthened particles. Okay, so microstructure of metal and ceramic composites which show particles of one phase strewn in the other is known as a particle reinforced composites. Normally these metal matrix or maybe the ceramic matrix composites are done using this type of composite materials. Okay, so where a method called powder metallurgy in a metal matrix composite is used to form a particle reinforced composites, where we are going to take the matrix and reinforcement in the form of particles in a powder form, and they are compressed and they are sintered at a high temperature to give a strength to the ceramic or maybe the metal matrix composites. Okay, so in particulate composites, the particles strengthen the system by hydrostatic correction of fillers and in the matrix by their hardness related to the matrix. Okay, so three-dimensional reinforcement in composites offers isotropic property because of the three systematically orthogonal planes. So where it is compressed, so the particles are distributed, okay, throughout the matrix material, and they are randomly distributed. So we can expect a strength in equal in all the directions. So the composite strength usually depends on the diameter of the particle and the interparticle spacing, the volume fraction of a reinforcement, and the matrix property influence the behavior of a particulate composite material, because the binding of these particles intact is the property of the matrix material. So the next category in that one is a viscous. Okay, so viscous reinforced composites. So where normally we go with a single crystal uh, grown for a particular application. Okay, so where these are nearly zero defects materials. Okay, so they are usually discontinuous and short fibers of different cross sections made from several materials like a graphite, silicon carbide, copper, iron. So typically the lengths are will be 3 to 55 nanometer in a range. Okay, so whiskers differ from particles in that way, like whiskers have a definite length to width ratio, okay, which is greater than 1. Okay, so whose tensile property, okay, will be extraordinarily limited or more than 7000 MPa. Okay, so whiskers are fine, small sized materials, not so easy to handle, and this comes in the way of incorporating them into an engineering metal to come out with a superior quality. Okay, so in the composite material. So nowadays the research wherever it goes like with the superior or high strength materials, so there we can go with the handling of a whisker. So now once we see these okay fibers, so again in the type of a fiber, okay, just to look into few examples, okay, in the fibers. So normally we are going to have a particulate, laminated, all those things. But in general, the major application in the reinforced materials is the fiber one. Okay, so where these things are going to have occupied the major portion in the production of the composite material. Okay, so we're going to take a few examples. So where the first example is a glass fiber. Okay, so it is generally called as a E glass. Okay, so E stands for electrical insulation. Okay, in general, the normal glass which we are going to use, or a C glass which stands for a corrosion resistant, or a S glass which stands for a high temperature application. Okay, so in general, in generic, so the glass fiber is normally used. Okay, so in order to use these many different types of glass fibers in a general application. So when we see the properties of a glass fiber, so common glass fibers are silica based oxides approximately 50 to 60%, and other oxides are being sodium, magnesium, aluminium. So over 95% of fibers used in a reinforcing plastics are glass fibers, okay, because of their inexpensive in nature. Okay, so their low density, resistance to chemicals, insulation capacity. Okay, so all these properties are added advantages to the glass fibers whenever we are going to choose them for a practical application. Okay, so although the one major disadvantage in a glass fiber is that prone to break when subjected to high tensile stress for a long time. Okay, and even with the temperature also. Okay, so when they are at a low temperature they will get brittle, and they are at high temperature they get a softened. Okay, so glass fibers are available in the form of a mats. Okay, so tapes, cloth, continuous, and chopped filaments, roving, and hands. So depending upon the what type, okay, a composite material needs, whether it needs a unidirectional fibers or a bidirectional like a match. Okay, so depending upon that one can choose the available glass fiber for preparation of the composite material. Okay, so next one very important example for a fiber reinforced composite is a carbon fiber. Okay, so which are obtained by subjecting the pan, that is a polyacrylonitrite, as a raw material which is subjected to stabilization, carbonization, graphitization in order to produce or in order to extract the carbon fiber into the carbon fiber from a pan, that is a polyacrylonitrite. Okay, so which is consisting of 91 to 94% of a carbon. Okay, but graphite fibers are over 99% of carbon. The difference arises from the fact that the fibers are made at a different temperatures. Okay, so now this pan, that is a polyacrylonitrite, is produced. The carbon fibers are produced from this one, which is subjected to a temperature of 1320. Okay, while the graphite fibers are produced at 1950 to 3000 degree Celsius. Okay, so now the properties of a graphite remains unchanged even at high temperature, but its willingness to react readily the most metals at a fabrication stage or during use at very high temperature is often a stumbling block. Okay, so normally we go with the these carbon fibers instead of these graphite fibers. Okay, so graphite fibers are some of are stiffer fibers known. The stiffness of the fiber is high as the graphite content, but the major drawback is the stiffness and the strength are inversely proportional to each other. So whenever you need to have a stiffness, then you have to compromise with the strength, or whenever you want a strength, you need to compromise with the stiffness. Okay, so forbidding the cost make the use of graphite fibers prohibitive. That amount which we are going to incur to produce these graphite fibers and use of that one, so is limited due to the production of those things is bit costlier. Okay, the carbonization and graphitization are time consuming apart from the demanding excessive energy, materials, and close controls throughout the process. So cheaper pitch based fiber are now being developed with the greater performance potential, and there are possibilities of increased use of graphite fibers also. So now how exactly we are going to produce these carbon fibers? Okay, carbon fiber from the pan, that is a polyacrylonitride. Okay, so there are three methods. Okay, there are three steps which are mainly important or which we are going to follow to produce the carbon fibers. One is a stabilization, okay, one is a carbonization, one is a graphitization. Okay, so you can say like a, so this carbonization is something where we are going to increase the carbon content in that one. So stabilization where we are going to heat this one with a high temperature, okay, for a proper alignment of the fibers, and graphitization again to increase, okay, the modulus of elasticity at the expense of tensile strength. Okay, so we are going to increase the stiffness by reducing the strength of the fibers. Okay, so you can say like the steps goes like this, like a acrylonitride polymerization, polyacrylonitride, that is a pan. So spinning acrylic fiber, so oxidation, oxidized fiber, so where we are going to remove the oxygen, that is hydrogen and nitrogen atoms or particles. So carbonization where we are going to align these fibers in a one direction by increasing the carbon percentage in that one. So graphitization, surface heat treatment and sizing. So where so either you can go with the high tensile strength fiber or you can go with the high elastic modulus fiber. So as we discussed, either you can get a high stiffer fibers or a high strength fibers. Okay, so one need to choose out of which one you want. Okay, whether your application requires a high stiffer carbon fibers or a high strength carbon fiber. Okay, so you can see the same process here also. So pan which is oxidized, okay, so and then the carbonized, then they are stretched in order to get a uniformly oriented and high strength carbon fibers. Okay, so there are three steps, okay, like as I said, the stabilization and carbonization, graphitization. Okay, so which are maintained or which are subjected at a different temperature to get the different properties and processes. Okay, so next example is aramid fiber. So aramid fibers are made up of aromatic polyamides which are long polymeric chain and aromatic rings. Okay, their structures are having a 6 carbon atoms are bonded to each other to combination of hydrogen atoms. So in aramid fiber, so these rings occurs and reoccur to form the fiber. So they were initially used to reinforce automobile tires. Okay, so normally they are having a very good wear resistance. Okay, so they are used in automobile tires. Okay, high strength application like a power boards. Okay, aramids have a high strength, high tensile strength, high modulus and a low weight. So impact resistance can be produced from the aramids. So the density of aramid fiber is less than that of the glass and graphite fibers. So means wherever there it needs an application of a light weight and a good strength material, so we go with the aramid fibers. So they are resistance they are fire resistant apart from being high temperature resistant and unaffected by the organic solvents like fuels. Okay, but their resistance in acid and alkaline media is poor. So they are supple and allow themselves to woven into a matrices by a simple process. So the processing of these fibers will be a bit easier. So aramid fibers have a negative coefficient of thermal expansion in the fiber direction, and failure of aramid fibers is unique. Okay, so one has to understand the failure of these aramid fibers, okay, to understand the behavior of these things in a practical application. So when they fail, the fibers break into small fibers which are like a fibers within the fibers. So this unique failure mechanism is responsible for a high strength, means they are not going to stretch and break into two pieces, but instead of that one they will break into small pieces, so which leads to again a particle dispersed strengthening. Okay, so which leads to high strength in the aramid fibers. So the last category in this, the last example for the fibers is a boron fiber. Okay, so where the boron is coated over a tungsten wire. Okay, so this one is called as a boron fiber. So normally boron is deposited on a tungsten and the process is continued until the thickness is achieved. Okay, the tungsten however remains constant in its thickness. The properties of a boron fiber generally change with the diameter, okay, because of the changing ratio of boron to tungsten. Okay, whenever we are going to change or increase the thickness, the content of boron will be increased, and whenever we are going to decrease the diameter, so the content of the boron will be reduced. So depending upon the amount of boron which is deposited on the tungsten filament, so the properties are going to vary. Okay, so they are known for their remarkable stiffness and strength. So their strengths often compare with those of glass fibers, but their tensile modulus is high, almost 4 times that of the glass. Okay, so boron coated with the carbon are much cheaper to make than boron tungsten fibers, but it is a low modulus elasticity often works against it. Okay, means wherever the application requires, okay, a low modulus, that is a high strength material, so then we can go with a carbon which is coated with the boron. Okay, so instead of a tungsten coated with the boron. Okay. So like that we can have plenty of fibers, okay, so which are having a very good properties. Okay, so again, so as we said, so it's a directional tailoring, we can say, or the properties which we want in a particular composite for a particular application can be tailored. Okay, tailored means it can be obtained by choosing a proper processing method and a proper fiber and a proper length of the fiber, okay, and the size of the fiber and the type of a fiber in the composite material. Okay, so these are the classification and a few examples of a fiber reinforced composite material.